Making sense of QFT. Lecture 8. Einstein's causality. This is the last lecture of our series about QFT. Here is the outline. First, we will recall that in the dressed theory, particles interact by instantaneous action at a distance, forces. But this is in obvious contradiction with Einstein's special relativity theory. This is an interesting paradox because we always insisted that our dressed particle theory is fully relativistic. Then how come we ended up violating the relativistic speed limit? First, I'll explain why the existence of this speed limit is inevitable in Einstein's theory. It relies on the fundamental and universal character of Lorentz transformations for time and position of events. But can we derive the Lorentz transformations in our dressed theory? The answer is yes, but only for non-interacting particles and events. Then we will conclude that for interacting events, Lorentz transformations are only approximate, and the Minkowski space-time concept is approximate as well. The next question: can we test these predictions experimentally? We will talk a little bit about the remarkable experiment of Professor Pizzella, which proves that Coulomb fields propagate faster than light. Finally, I'll formulate conclusions for the entire series. In our previous lectures, we established that dressed QED is a relativistically invariant theory. Most importantly, we proved that Poincaré commutators are satisfied exactly. Moreover, both postulates of Einstein's special relativity are satisfied as well. The first postulate about the equivalence of all inertial frames of reference is in the basis of Wigner's theory of symmetry in quantum mechanics. We also showed that the second postulate about the invariance of the speed of light is a trivial property of massless particles, photons. But we also know that the universal speed limit c is the most important result of Einstein's theory. So we might expect that this speed limit applies to the dressed QED as well. However, our conclusions were exactly opposite. In the dressed theory, particles interact via instantaneous forces. This implies faster than light signaling. How is it possible? This is the paradox that we will try to resolve today. Let me now explain why special relativity insists on the speed limit. Suppose that we have two observers, Alexei and Boris. Alexei is at rest, and his word line in the Minkowski spacetime is shown by the blue line here. His coordinate axes are x and ct. On the other hand, Boris is moving away from Alexei with high velocity, so his green word line is inclined and his coordinate axes x prime and ct prime can be obtained from xct by a shift and a pseudo-rotation. Now, suppose that Alexei and Boris are implacable enemies and they decided to resolve their conflict by a duel. As the dual weapon, they choose pistols shooting superluminal bullets. For simplicity, let's even assume that the bullet speed is infinite. So Alexei's bullet propagates parallel to the equal time x-axis. And Boris' bullets also move parallel to the equal time axis. But this is his x prime axis, which is inclined with respect to Alexei's axis. The fact that equal time axes of different observers may not be parallel is an illustration of the famous relativity of simultaneity. Now, the duel proceeds as follows. First, Alexei fires his gun. This event happens at point A of the Alexei's word line. The superluminal bullet hits Boris at point B of his word line. But Boris is only wounded, and he fires back immediately. Boris' bullet hits Alexei at point C of his word line and kills the man. Now, you may reasonably ask how come that Alexei was killed at point C and then was able to fire his weapon at a later point A? That's impossible. And you are right. This is a causality paradox which special relativity resolves in a radical way. It simply forbids any signal to propagate faster than the speed of light. Now, how reliable is the proof given above? It depended on the so-called pseudo-rotation of coordinate axis, which was just a way to express Lorentz transformations of special relativity. But are we sure that Lorentz transformations were proved rigorously? Indeed, in Wigner-Dirac-Weinberg quantum mechanics and quantum field theory, we never mentioned the Minkowski spacetime. Yes, there were arguments T and X of the quantum fields, and these arguments transformed by Lorentz formulas under boosts and rotations. However, as we mentioned earlier, these arguments are just dummy integration variables which play no role in the final S matrix and in experimental predictions. However, in the dressed theory, we can try to derive Lorentz transformations. That's how we can do it. We can switch to the classical, non-quantum approximation, where particle trajectories make sense, and define events localized in space and time as intersections of such trajectories. Then each such event in each frame of reference can be characterized by its time and by the position of involved particles. And using representation of the Poincare group, we can transform these quantities from one reference frame to another. So this sounds like a good plan. Let's see what we get. We begin with a simple case of non-interacting particles whose trajectories intersect at a point with coordinates ct and r. From the point of view of a moving observer, this intersection occurs at point ct prime and r prime. The calculations are not difficult, and the result is that the two sets of coordinates are related to each other exactly by Lorentz transformation formulas. These are the explicit equations connecting CTR and CT prime R prime. Here, theta is the rapidity parameter which we discussed in our first lecture. But if we repeat the same calculations for a couple of particles interacting by addressed potential, we'll find out that the transformation law becomes rather complicated. It will depend on the type of interacting system, on its state, on the strength of interaction and other details. The reason for this complexity is the presence of interaction ZD in the boost operator of the addressed theory. This result has been known in the literature since 1963 under the name of Curry-Jordan-Sudarshan no interaction theorem. This means that Lorentz transformations are not exact and universal. Minkowski spacetime is not a rigorous concept, and special relativity requires a major revision. In particular, there is no rigorous proof of the contradiction between superluminal signals and causality. But you may say, wait a minute, special relativity passed all possible experimental tests for more than 100 years of rigorous studies. How dare you say that it is inaccurate? The point is that almost all experimental tests dealt with properties of light or massive particles that do not interact with each other. In such situations, predictions of the new theory are the same as in the traditional special relativity. There is, however, one type of experimental tests where we deal with particles whose interaction lasts for a time that is long enough for observations. This is a slowdown of decays of fast-moving particles. The best accuracy of 0.2% was achieved in measurements of the decay law of relativistic muons. However, estimates show that corrections introduced by interacting boosts are many orders of magnitude smaller. So experimental verifications of these predictions are impossible today. This was a bad news. But there is also a good news. There is an experimental effect whose descriptions by the old and new theories are very different, and these differences can be observed in the laboratory. I am talking about the Coulomb field of fast-moving particles. On the left, I drew electric field lines around the point charge at rest. It is well known that they form a spherically symmetric pattern. But if the same charge is moving, then the field lines become compressed. The Coulomb field of a very fast charge forms a thin pancake oriented perpendicular to the direction of velocity. It is well known that this simple picture is valid only for charges that were in the state of uniform motion for a very long time. But suppose that we have a fast charge that emerges suddenly from the surface of a conductor or from a metallic pipe of particle accelerator. The signal about the charge being released into the open space cannot propagate faster than light, according to special relativity. Then the Coulomb field pancake cannot be formed instantaneously. From this figure, it's clear that the Coulomb pancake grows gradually in a linear fashion. Its radius r is equal to the traveled path L multiplied by the ratio of the particle mass to its energy. For relativistic electrons produced by modern accelerators, this ratio can reach values much lower than unity, and this means that the electric field around the electron bunch grows very slowly. If we could register this slow formation of the Coulomb field, this would be an indirect proof of the limited speed of propagation of Coulomb forces. But if the field emerges instantaneously in the entire space, we will have to conclude that the propagation speed is infinite. This was the idea of an experiment performed in 2012 by the group of Professor Pizzella at the Frascati nuclear lab near Rome. They showed bunches of accelerated electrons in the experimental hall. The beam line is shown here by the red arrow. The space around the beam was filled by many electric field sensors with good time resolution. Positions of the sensors are shown by blue stars here. The calculation in the lower right corner shows that with the electron energy of 500 mega electron volts, the radius of the Coulomb field pancake was expected to be just 6 millimeters. This means that the pancake was not wider than the red arrow in the figure, and according to the classical electrodynamics, the electric field sensors should not register any signal. However, experimental observations were completely different. Quite significant signals were detected, as shown by the green lines. Their forms were the same as if electrons were in a permanent state of uniform movement. In other words, instead of the gradual pancake growth predicted by classical electrodynamics and special relativity, the pancake emerged immediately in the entire space after the electron bunch left the accelerator pipe. This is a strong evidence in favor of the instantaneous propagation of the Coulomb field and a good reason to reconsider the validity of special relativity and the Minkowski space-time picture. Let me now formulate the conclusions that follow from all our lectures. Hopefully, I was able to convince you that there are good reasons to believe that the primary ingredients of nature are point-like particles obeying the laws of quantum mechanics. The particles interact with each other directly by potentials which obey the requirements of relativistic invariance. They act instantaneously at a distance. They depend not only on particle positions but also on their velocities. They contain terms that can change the number of particles. This is a dressed particle theory which has a number of advantages with respect to quantum field theory. In the dressed approach, there is no need for renormalization, while the S matrix is exactly the same as in the renormalized QED. So the dressed theory enjoys the same perfect agreement with experimental observations. The Hamiltonian of the dressed approach is finite, so energies and wave functions of bound states can be obtained by the diagonalization of this Hamiltonian exactly as we did in non-relativistic quantum mechanics. The time evolution operator can be constructed, and time dependence of states and observables can be studied and compared with experiment. Our approach has demonstrated that the Minkowski spacetime of special relativity is an approximate concept. It is okay to use this concept when particle interactions are weak, but in the general case, things are much more complicated. Remarkably, these predictions can be verified right now by studying electric fields around charged particles in accelerators. These investigations can be done with equipment available at many particle accelerator sites. One example was the Pizzella experiment performed 10 years ago. It's very important to continue this research. This was my attempt to make sense of QFT. Thank you and goodbye.